Hey everyone, thanks for coming. Wow, full house. First off, if you're looking at my title and you're like, wow, I only know what California is, don't worry, we're gonna go through and explain a bunch of these things. I also want to acknowledge my mentors, Magali Barba and Christy Tiampo, who are in the audience. Even Enrique, my communications mentor, made it out today. So to start off, my project this summer had two goals. The first was to basically figure out the improvement of interferograms through using high-resolution DEMs. And DEM stands for Digital Elevation Model, and we'll talk more about those later. My second goal was to compute a new creep rate from Sentinel-1A satellite data, and we'll talk more about that too. So let's start out with creep rate. So here's a map of the Bay Area, and that black line in the middle of the map is the Hayward Fault. And we're pretty zoomed out. This is a pretty big scale. The scale bar on the bottom left shows 30 miles. So we're talking about a big area here. So fault creep is basically an aseismic movement across a fault. So when most people think of earthquakes, they're thinking like a big displacement, like this big shift. But with aseismic creep, it's moving really slowly. So it's like indiscernible if you're living on top of it. And there's a lot of people living on top of this too. There's 1.6 million people living in Alameda County, which underlays the Hayward Fault. Apart from that, there's the greater Bay Area, which has at least 7 million people. So 25% of the strain between the Pacific plate, which is the largest tectonic plate, and the North American is accommodated through this fault here. And the Hayward Fault is pretty frequently overshadowed by the San Andreas Fault, which is a little bit further west. Now that we understand what we're trying to get a better view of, let's go through and look at how INSAR works a little more. So D-InSAR stands for Differential Interferometric Synthetic Aperture Radar. And to better understand it, I first kind of wanted to like reintroduce a wave. So there's two parts to the wave that we need to focus on. So one is the amplitude, which is the height of the wave, and two is the phase. So phase is a little tricky because it refers to a position on the wave from 0 to 2 pi. And we'll come back to that when we look at more at interferograms, some of our products. So the way differential D-InSAR works is there's basically two satellite passes, and you get a SAR image from each one. So on the first pass, in our image here on the left, the Earth's surface would be at the point where, sorry, it'd be basically represented by the yellow there, and the second one would be represented by the orange. Having these two passes and shooting down active wavelengths allows us to map deformation on the Earth's surface. So now that we have a basic idea of how INSAR works, let's look through a basic example. So here's two SAR images from Iran. This was a study done by Pritchard in 2006. And so again, we have amplitude and we have phase. So there where we have the 10 kilometer mark is actually water that's part of the Persian Gulf. And we can actually see hills in the amplitude because it's the reflected, basically, quality of the light. For the phase, it really looks like static. You can't really see much in the phase images. But when you differentiate, when you basically subtract the second phase image from the first, you start to get an image. So when we processed this, we used ICE and Giant software developed by JPL, which is a little bit different from what is used in the study that I'm showing here. But we start to get an interferogram. So this one here by itself doesn't really give us too much info. So there's extra processing that goes on. So you need to correct for spherical Earth, and you can remove atmospheric and topographical effects. So half of my research is looking at this step here, where we're comparing, where we're looking at the removal of topographic effects. And we'll get back to that. So these are some of the basics for INSAR. We'll take a look at where we got our data. So here we have another map of the Bay Area, and these colored frames basically show us where our SAR images come from. And the image in the middle shows basically our area of interest. So some of these only get half of the image. So these are stitched together to get the full area. And again, we get our data from the European Space Agency. They have a satellite called Sentinel-1A. They also have one called Sentinel-1B. And in the future, we may be looking at that one as well. So our results so far have been constructed from 17 SAR images, spanning from February 22nd in 2017 to October 9th. Now that we have a better idea of where our SAR scenes came from, let's apply these back to our goals. So our first one was looking at coherence. So we want to know basically how well our InSAR images work. So it's basically a measure of how well they represent the deformation. So to do that for this goal, we first have to upsample our DEMs. And we do that kind of how this image in the right is showing. So we start with a 3-meter DM. So each pixel is a 3 by 3 meter pixel, and we upsample it. So we go from 3 to 9, 12, 30, and 90. And we use these different resolutions to basically see the change that they create in our processing. So what does that look like? Well, if we zoom in really closely, here's a view of the Oakland Airport, which is alongside the Hayward Fault. And I like this image because you see some hills in the background, and you can really see the difference in resolution between the two slides. So yes, on the left, the 3-meter DM, you can see the runway, you can see a little bit of a stream coming out of the mountains. And on the right, at 90 meters, you really don't see very much of it anymore. There's definitely some hills going on. So then we get products from using these DMs. And if you're looking at these two, they look really similar. So basically what this map is showing us is it's showing us relative coherence. So the purple means it has low coherence, and we have that all over the water. And the yellow color is showing us where we have a readable signal. So at this point, this goal has been a little bit inconclusive. We're trying to get a percentage of coherent pixels. And so far, we haven't been able to completely interpret our results. Currently, we have the best results around a 30-meter resolution. And we suspect this is because the processing uses around 20-meter pixels before interpolation. Along the way to getting these results, we found a really big difference between these images here and the standard that's provided along with ICE processing. So on the left, we have an interferogram from our upsampled DM, and on the right, we have one, the standard, which is from the Satellite Radar Topography mission. And here we can see a pretty big difference in the topographic signal. So when I was showing you guys how InSAR worked, one of the things that I mentioned was how we try to remove the topographic signal so we can get a good read for the movement on the ground. So in this area shown by the boxes, we can see how this area in the hills has almost like a shimmering kind of effect on the image on the right, where we're getting a lot of residual topography. And this signal makes this image difficult to use because it's giving us a read for the topography as opposed to ground deformation, which is what we're ultimately trying to measure. Then we see a big difference in coherence as well. So again, for these two bottom images, purple is not the color we want. We can't use purple because we don't have a good grasp for the coherence. So again, on the left, we get better coherence through the hills. This is a hilly area with vegetation, which is why some of these effects are happening with the standard. And then on the right, we basically don't get a coherent image, basically on the entire right side of the fault. So while this wasn't the original research goal, we definitely found these clear differences between the standard and the upsampled DEMs. And when we're using both of these are both at 30-meter resolution. So they should be a lot closer together. Our second goal was to compute Hayward Fault creep rate using the Sentinel-1A data. And what this map basically shows is the overall cumulative displacement. So this figure on the right represents 1 pixel out of the thousands of pixels that we have going on in our scene. So the dots in red basically show us the displacement in centimeters across each date. So it's a time series. And then the blue is basically the best fit line for that pixel. And to have pixels on this cumulative displacement map, we need to have coherent pixels all the way through the time series. So to have this complete of an image at this point is really promising because we have a really short time series. So let's see. So yes, each of these points are basically represented, the points on the figure on the right are spaced out by 12 days, which is when our repeat interval was for the satellite. So the tricky thing with early INSAR results is that I can't call this movement displacement. I have to call it line of sight displacement because it's movement in relation to the satellite's view. To get a better read, to be able to separate this into horizontal and vertical motions, what I need to do is get a different view from this. So how will we do that? Through continued work. So this figure on the top shows us basically the data availability for track 115, which is what I used to do the study so far. And that little green bar basically shows the data that we've processed, and the blue is the data that's out there. So the right side of the blue is going to continually move as time passes because they update it regularly. So there's still a lot of data to be processed. Once we do that, there's also track 35 and 42, which overlay the same area, and we can use these to better understand the motions that we're seeing, the displacement motions. Apart from that, we can look at coherence based on the slope. So we can compare the coherence that we're seeing on the slope of the DEM on the right side of the fault, and we can get an understanding of how it acts when you have, say, 10, 20, 30% slope. Finally, an updated version of this presentation will be appearing at AGU, so come find me. In conclusion, using a higher resolution DM allows better tracking on both sides of the fault, while a lot of previous studies only had a coherent signal on the western half. When we originally got these results, we were pretty surprised how clear the signal was for how short our time series was. A lot of time series really need more time to create a coherent signal. So with our time series, we're optimistic about future results because we have had clear data so far. We need more time. Then with the unsampled DEMs, we're still working on the pixel coherence, but that's okay. There's plenty to be done there. And then we can also apply this to other areas, not just the Hayward Fault. That being said, I will now open up for questions.
And we're going to ask, when people ask questions, to use the mic so that those who are online can hear.
Great job on the technical aspects of the work you were doing. I have a question that's more related to the implications from a geophysical and seismic hazard perspective. So it was my understanding that the Hayward Fault in that region is mostly locked and therefore has very high seismic potential because it hasn't ruptured for a few hundred years. I don't know the exact dates. So what percentage of the expected motion is being taken up by creep from your analysis?
What percentage of the expected motion is taken up by creep? Yeah.
You know, we know what the full plate rate is in North America. We know how much
Yeah. So that's a good question, and I don't feel that my research itself is answering that, but having a better map of the deformation on both sides of the fault will allow for a little bit better modeling. So you're completely right that it's locked in several areas, and there's different slip rates in different areas of the fault. This image starts to kind of represent that a little bit. However, like I was saying, we need a little bit of a longer time series to really accurately answer that.
Again, really nice presentation there. And one of the questions I had was, how does vegetation impact the coherence? And if you could review like the time dates that you were getting your images.
Sure. So let's see. So vegetation is tricky because it basically changes shape faster than the ground does. So, you know, a tree might, so my scans are 12 days apart, and depending on what kind of radar we use, this particular study uses C-band radar. So we're looking at a smaller unit of deformation. And if a tree grows too much or there's too drastic of a change, we have decorrelation happen. So we can no longer track the same pixel from one scene to the next because it's too drastically different. So that's why vegetation makes it tricky, because it's difficult to identify the same tree or bush, whatever it might be, from scene to scene. Yeah.
So in other words, with the Sentinel-1A, its signal is not, it is being reflected by the trees. It's not making it through the vegetation.
Let's see. I'm thinking back to the several types of radar, and I believe that I really want to defer to one of my mentors on this, because there's several that are used for vegetation purposes, but I'm not positive on this one. Okay, sorry.
Again, great job. Do you have a plan to independently monitor the area using maybe GPS or use available GPS stations around that area to monitor the formation?
That's a good question. So there's ongoing monitoring of the Hayward Fault. There's several creep meters on the ground, for example, and recently a GPS study was published looking at the Bay Area. I kind of think of this as like a complementary, it's using a different method to track the deformation along with points on the ground through the creep meters as well as GPS.
Great. Any other questions? All right. Thank you, Joe.
All right, thank you guys.